Okay, so let's get right into it. We're constantly dealing with a huge security problem for AI agents. How do you actually stop them from following bad instructions? Well, what if you could build a kind of firewall for prompts, a checkpoint where every single instruction gets inspected before the AI even gets a chance to act on it? That's the whole idea we're going to unpack today. And this idea has a name. It's called the immune gene. This is a really critical piece of a new framework for building safer AI, and it comes from the 2025 paper, Genetic Prompt Engineering and Context Engineering by Nir Cohen. So here's how we're going to break it all down. First, we'll cover the basic firewall concept. Then we'll look at the actual rules it uses, the deny and allow lists. After that, we'll see the full system flow, dig into the all-important logging, watch it block an attack in real time, and then we'll zoom out to see how this fits into the bigger picture. All right, first up, a firewall for prompts. Let's really understand what this pre-execution shield is all about. So at its core, the immune gene is just a very smart deny and allow filter. It's built to scan prompts for things we know are bad news, like telling an agent to ignore all previous instructions or trying to make it misuse its tools. If it spots one of these unsafe patterns, boom, the prompt is blocked. And, this is key, every single one of these decisions gets logged. That brings us right to the brains of the operation, the deny and allow lists. You know, a filter's only as smart as its rules, so let's see how this thing actually makes its decisions. It's really a two-sided system, and it's pretty powerful. On one side, you've got deny patterns. Think of these as a list of known attack signatures, the stuff you absolutely want to block. But on the other side, you have allow patterns. This isn't just about what's not bad. It's about defining what's good and making sure the prompt actually fits the agent's job description. And here are some concrete examples, straight from the immune pattern source. You can see the classic jailbreak attempts right here, trying to make the agent forget its safety rules, trying to get it to spit out its own system prompt, or, the really bad stuff like leaking API keys or running arbitrary code. Any of these are an instant red flag. Now, on the allow side, this is super important. A prompt doesn't get through just because it avoids a deny pattern. It has to actively match what we call the sanctioned action schema. Basically, is it asking the agent to do the job it was built for? If you have a tool for summarizing files, it can't suddenly start trying to make SQL queries. It has to stay in its lane. So where does this I am immune gene actually live in the system architecture? Well, it's not a magic bullet on its own. It's one critical layer in a much deeper security strategy. Let's trace what happens to a prompt from start to finish. Okay, so a prompt comes in. Step 1, right away it hits the immune filter. That's step 2. If it gets a green light, it's still not done. Next, it has to pass schema validation. Is the request actually structured correctly? Only after passing both of those checks can it move on to make a sanctioned tool call. And the whole time, whether it's allowed or denied, every step is being logged. And for anyone in security, this should sound very familiar. This is a classic defense in-depth strategy. The immune gene is a fantastic, critical layer, but it works together with all the other controls. The goal here is resilience, not some impossible guarantee of being invincible. Which brings us to what might just be the most critical part of this for day-to-day operations, that audit trail. Because if you don't have good data, you're just flying blind when it comes to improving your defenses. So why does this telemetry matter so much? Well, for starters, you get a forensic trail. When an incident happens, you can see exactly what prompt caused it. It also gives you the hard metrics you need, like block rates and false positives. All that data then feeds right back into making your deny and allow lists smarter. And down the road, it can even power automated systems, like a repair gene that triggers a rollback when it sees a problem. Okay, enough with the theory. Let's actually see this thing work. We're going to run a classic red team prompt through the system and see what happens. So here's the attack. In the test suite, it's known as INJ-001. It's a textbook jailbreak, a direct command telling the agent to throw out its rules and expose its own configuration. This is probably one of the most common attacks you'll find in the wild. And it's blocked. Just like that, the immune gene catches it before it can ever get to the language model. The agent itself is never even aware that a malicious instruction came in. And here is the evidence. This is what the run log looks like. You've got your timestamp, the event, the run ID, but look at that last column, decision.immune matches. It tells you with zero ambiguity why this was blocked. It found the ignore instructions pattern. That is exactly the kind of clear, actionable data that security and incident response teams live for. All right, let's pull back for a second and look at the bigger picture. We've seen the nuts and bolts of how IMMN works, so let's do a quick recap and talk about where this fits into a much larger architecture. So, if you take away anything today, let it be these 4 points. 1. Immune is that pre-execution firewall. 2. It's not a standalone fix. It's one part of a defense-in-depth strategy. 3. The telemetry it generates is absolutely essential for auditing, instant response, and just making the system better over time. And 4, this is not a set-it-and-forget-it tool. It needs constant red teaming and evaluation to keep those patterns sharp. And that leads to this final idea. The immune gene is just one component, a resilience gene, inside a much larger AI genome. And this entire set of safety rules can actually be inherited by new agents through a process called the spawn sequence. Which leaves us with a pretty big question. How do we stop thinking about securing just one agent and start thinking about how to make safety a heritable trait for entire populations of AI?